Right. So there's some rules, or at least there's one rule that I wanted to mention before we begin, and it's sort of spurred by, I guess, my other class. So just in case like you didn't quite gather from the slides, there's the operation of taking a derivative is actually linear. So you've got this property ddx of, if we have, let's let k be a number, I guess, and then I'll write it in full, f of x plus g of x. This, because the operation of taking a derivative is linear, just like how I should have said, I think I said that like taking a limit, the operation of taking a limit is also a linear kind of thing. You pull out the scalars and you can also factor, or you can split the operation over the addition and subtraction. So this expands out into something like this, ddx of g of x. Or if you wanted to abbreviate this, you would have, oops, what am I doing? K and then f is a function plus or minus g. You're taking the derivative of that. That would be equal to k f prime plus g prime. Okay. So yeah, this is something that I didn't mention, but that we actually implicitly were using for some of the something back here. Like, yeah, oh, this, yeah. With this problem, the fact that I just like thought of the derivative term by term, that's only allowed because we know that taking the derivative actually splits over each term. So we can just consider things term by term. So that, along with the power rule, and then of course we began introducing the product rule and the quotient rule. So just quickly recap, if you have a product of two functions and you're trying to take the derivative of that, well, you've got this rule, which is not the rule that you would like, but this is the correct rule. And then for quotient rule, well, you've got a function on top divided by a function on the bottom. And you have this kind of thing going on where usually the way it's taught is that you keep the order from product rule the same. You have to remember that it's in this particular order, and then you just turn the plus into a minus, and you have to remember to divide by the denominator squared. The g in the denominator gets squared. Okay, and those are the rules that we need so far. And later on, probably the next week, you'll learn chain rule, and then you start dealing with derivatives for the trig functions, inverse trig functions. But for now, we're just working on this, and I guess we'll continue where we left off. So, oh, this is where we left off, actually. We didn't do part C. All right, so for part C, what I want to do is I actually want to introduce the generalized product rule, because this is actually a product of three different functions. Another way you could do this, actually, is you could multiply these two together, and then you've got a product of two functions, right? This will just be some x squared plus 9x plus 20. Yeah. So you could do that, and then you could take the derivative of the product of two functions, two polynomials. But I may as well, I actually don't know how, like, which approach you're supposed to take for this, but we can introduce generalized product rule. And I think the best way to introduce it to you is actually to show you why it's true. So we're going to use the abbreviation because I don't want to put all these parentheses, FGH, and take the derivative, right? So we have a product of three different functions. Well, the way you should think about this is to group two of them together and then apply the usual product rule on this multiplication. So I'm going to put that dot there to signify this is the multiplication that I'm going to expand out. And so what do we get? Well, according to product rule, it's derivative of the first thing times the second plus the first thing times the derivative of the second. So we would end up with this. And now notice that this actually expands out because we need to apply product rule to this because this in itself is a product of two functions. And so when we expand that out, we get f prime g plus f g prime. And this is the expansion of just that derivative. So this is actually all being multiplied by h. And then we just copy down the other guy. And I'm going to suppress that dot now, so I don't need that dot anymore. And then now you can see if I distribute that h, f prime g h plus f g prime h plus f g h prime. Now notice the pattern, right? What's happening in each one of these terms? Well, one of the guys is getting their derivative taken, and then the other two are just the same as the original. Right? So this you can hopefully see now. This is just going from here to there. You can just sort of see the pattern, and then you can generalize it even further, right? If the generalization is exactly the same. If you want to show that it's true, then you have to just do this, but with even more letters. All right. And so just using this idea, I can write immediately what the derivative will be for this problem. So first I'll take the derivative of the x plus 4. That'll just be 1. Do I want to write the number 1? Yeah, maybe. Why not? Just to show my work a little bit. Squared plus 6. And then, well, next I need to take the derivative of the x plus 5. That's also just going to be 1. So, but maybe I will actually write 1. Right? Show my work. And then the last guy, I've got the x plus 4, x plus 5, and then a 2x. So you should know that the derivative of this is, of the x squared is the 2x. Okay. And if you wanted to, you could clean it up, but I'm just going to leave it like that. All right. Any questions on that? No questions? Okay. All right. Then number 7. Let's see. So the idea is that we actually just take the derivative of this and then we'll plug values into it. So this is just reading off the product rule. Maybe I'll write it like this. So I guess normally what you would do is you would first take the derivative and then you evaluate at 2. Would it be the fun? Would I clean it up? Oh, so in terms of the only reason to clean it up would be if you're actually going to use it for something, like if you're going to compute something further with this. Otherwise, I think it's actually more helpful to keep it in kind of the format that shows how you arrived at this answer, which is, just by showing it so that you can see like this is coming from the product rule. So I would leave it like this. I would only clean it up if I need to do something else with it. And I think there is maybe, no, there isn't an example in our homework for the, well, eventually you might see it. It's like if you are going to take like another derivative, for example, then in that case, it can make sense to clean it up before you go about taking another derivative. Yeah. Okay, but we're not doing that here. So. All right, I was saying something about this. Right, so taking the derivative of this and then evaluating at 2 is the normal way you would do this, but I'm gonna combine the 2 steps in one here. So product rule is gonna say f prime g, but I'm gonna say we're plugging in at 2, so we may as well just write that. F prime at 2, g at 2, plus f at 2, g prime at 2. Okay, and so now we can see we're just reading data off of our table here. So this is going to be f prime at 2 is just going to be 2 times g at 2, which is going to be 7, plus f at 2, which is 5, times g prime at 2, which is 6. And so we get 14 plus 30, which is 44. Yep. Yeah. and also b prime of 1. So this is a quotient, so we're just using quotient rule. So using my version, I go down to up, and I do g at 1, g at 1, f prime at 1, minus, what is it? F at 1, g prime at 1, all over, and then I had to square the denominator. So I have g of 1 quantity squared. Okay. And now we just plug things in. So g at 1 is 4 times f prime, which is 1 minus 3 times 2 over 4 squared, which will be 4 minus 6 over 16. That's right. Negative 2 over 16, which is negative 1 over 8. Okay. All right. Any questions on that? Okay. So number 8 is maybe a little bit trickier when it gets to D, I would say. Also maybe a little bit when it gets to C. But before that, it's pretty straightforward. So find the formula for the average cost. You're told that the cost is a function C of X. You want to create a formula for average cost. Okay, well, how do you do an average? You normally divide by the number of items. So this is the formula that you would come up with. And then how do you find a prime of X? This is really just asking you to take a derivative, and it's sort of noting that you're going to write something that involves these three kinds of things: X, the function C, and the function C prime. Okay, well, that is exactly what you're gonna get when you just do a quotient rule. So we're gonna do a quotient rule. We get X times C prime minus C times, and in this case, there's a 1 here because the derivative of X is just 1 all over X. Yeah, you can just, well, over X squared, square it. And pretty much you can just leave it like that. Now the analysis of when is it positive and when is it negative, that's where you have to think a little bit. So notice that because X is squared in the denominator, that's always going to be positive, so we can kind of ignore it. So it's going to matter, the numerator is what we have to consider. And really we're trying to figure out, like, how does X times C prime compare with C? Okay, so we can kind of do the same process as I showed you like last class, where you set the thing equal to 0, and then you solve. And this is sort of like what how you would mark things on the number line, except it's a bit more abstract, right? Because we don't really have numbers here, so it's kind of maybe a little bit harder to tell. But there is one thing kind of interesting that you kind of need to be able to see this, which is that if I divide the X here to the other side, I'm gonna get this identity. All right, and this is actually what C and D are all about, is actually spotting this little identity. So let me use a different color and actually like note certain things. So notice if this were greater than, this would also be greater than, this would also be greater than. And if it was less than, then all of them would also be less than. So that's why we can actually come over here for C and say a prime of X is greater than 0. When does that happen? Actually, do I have this written the right way around? Not necessarily the right way around, but that's a prime of X is greater than 0. A prime of X, wait, a prime of X, a prime of X. Oh, okay, yeah, this guy is a prime Actually, this is A prime, essentially. So this is greater than 0 when xc prime of x is greater than c of x, which is the same as saying c prime of x is greater than a of x. Okay, this is what these three lines are actually telling you. And the rate of change of average cost, that's how you would say this, pronounce this. That is when, and then I just would copy this whole thing down again, except flip the inequality, which happens when rate of change of cost is less than the average cost. Okay, and now D is just trying to make sense of why this, like intuitively, why should this make sense? And the thing I wrote here, I think it makes sense. I don't know. It's up to you to think about it, I guess, and make it make sense for you. But so what I wrote here is if the change in cost is greater than the average cost at a given point in time, I guess, then you would expect that this pulls out the average cost up. Expect it to pull average cost up, which is sort of translating why this statement gives rise to this. Yeah. And then vice versa, if the change in cost is less than the average cost, then you expect it to pull the average cost down. Okay. So does that make sense to you guys?
Yeah.
Okay, good. How much more do we have left? 9, 10, and 11 be done. Okay, yeah, I've got plenty of time. Right, so 9 is just a really nasty problem because you have both a product rule on top and a quotient rule overall, right? Okay, good. Okay, so yeah, so we have to actually use both product rule and quotient rule together. The way I would think about this is the quotient is the thing that happens last. So it's the first operation that we need to apply derivative to. Okay, so maybe I can abstract it out by doing like this. Okay, it'll be harder to express this when I'm actually like using these actual polynomials. But so you see that like the first thing you want to apply derivative to is the quotient. So you use the quotient rule, which is going to say h prime times fg minus, is that right? No, it's not. Fg prime, yeah, and then minus fg times h prime all over h squared. But then here we've got product rule, so we actually need to expand that out. So it's going to be f prime g plus fg prime minus like that. And well, whether or not you want to distribute that h, I think it's better if you don't. Yeah, I didn't do that. I just had a big set of brackets around it. But so we have to basically do this, but with these polynomials in mind. Okay, so let's go ahead and do that. So equals 3x plus x minus 2. So I'm copying down the denominator first, and then I take the derivative of the numerator. which is rather lengthy. Derivative of the numerator now, I think there's a product rule that's happening, so I have to now put myself in the mind of doing product rule. So derivative of this is going to be, well, to start off with, you would think of this as x to the 1/2 power, and then you would use the power rule, which would give you 1/2 x to the negative 1/2. But I'm gonna say that if you do derivatives long enough, you kind of get used to this little pattern that the derivative of this guy is 1/2 radical x. So I might express it like that instead of this way with a fractional power. I think I may as well do that here. Give myself a bit more space. Okay, and then derivative of the 2x squared is 2x. Okay, and that was the first half of product rule. I have to, well, after I copy this actually, that'll be the first half of product rule. And now the second half of product rule plus, copy this guy down, take the derivative of that guy. Square root of x plus x, or yeah, squared times, and then, so power rule on this, 5x to the 4. And then this is going to be 7, and then 5 disappears. You take its derivative. Okay, and that closes the product rule. That closes taking the derivative of the numerator. So this was all the first half of the numerator of quotient rule. Actually, I shouldn't close this parenthesis, should I? Should I? Wait, no, I do close it. I do close it. Then I have minus. Okay, minus. Yeah. We're gonna have a really big denominator that wraps over 2 lines. Okay, so minus, and then numerator times derivative of denominator. So I copy numerator down. Times, and now derivative of the denominator, 3. Well, it's going to become a minus because we take the product rule of that, or not product, the power rule of that. It's going to be a minus 2x to the negative 3rd. Okay, so this is the numerator for quotient rule. We have a very big division sign, and then we do denominator squared. Yeah. So that, all of that is the answer for 9. So yeah, it's pretty unappealing, but yeah, that's the answer. Okay. For number 10, so this one is pretty simple, actually. The only thing to really note is you should understand what this symbol here means. It means you're taking 2 derivatives, right? I was gonna say maybe something about like why this notation came about, but I don't know if you guys really care about that. But just know, like, yeah, you expect that the number shows up on the top and the bottom like that, and that means you're supposed to take the derivative of this. Okay, so first we're gonna take one of the derivatives, and well, I can write it like that. So basically, we kind of peel off one of the derivatives and we actually apply that, but then we're going to have another derivative operation that we have left to do. So I can write it like this, and then let's see, 15x squared minus 37. So that was the first derivative that we just took, and now we can go ahead and take one more derivative, which is what the symbol, what this expression is saying, right? Okay, well, taking one more derivative, we'll get 30x. And that's our answer. Okay. So that was way easier, right? And then here's the very last problem for today, unless you guys want to throw me extra problems. Blah, 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 position, double second derivative is acceleration, find the acceleration at 8. Okay, so the problem is actually asking us, maybe I'll put that in a different color, but it actually wants us to find s double prime evaluated at 8. So that's what we're going to need to do. But we'll start by taking 2 derivatives. Okay, so s is given. So I'll start by saying, what is s prime of t? Okay, so we take the derivative of this t to the 4/3 power. That's going to bring the 4/3 out. we have t, and then we subtract 1 from it. Okay, so hopefully everyone knows how to subtract 1 from a fraction. You can always mess up on that if you aren't paying attention. And now we take one more derivative of this. And we're going to get, so another 1/3 comes out, and we get 4/9. We just multiply the numbers together. And now this power, well, if you're paying attention, you get -2/3. Okay. And so this is what we actually need to evaluate at the value t equals 8. Okay. So maybe the next question is, how do you actually evaluate this guy at 8? So what I would do is I would take the radical first, right? This 1/3, this 3 in the denominator is actually a cube root. So really, I would interpret this as taking the cube root and then taking it to the negative second power, which negative second power also you should know is you square it and it's in the reciprocal. It's in the denominator. Okay. So first thing I do is I take the cube root. I'll get 2, and we're raising 2 to the negative second power. And this is just right. I square the 2. I get 4 in the denominator, and then of course we can multiply things. And we have units as well. So also just double check yourself on units. If you're doing feet and you have seconds and you're talking about acceleration, then it's feet per second squared. So this is our answer for number 11. Okay, so that's the whole problem set. Are there any questions? Well, if not, then I'm gonna stop the recording here. Oh, okay, question. Can I explain more on how to get the derivative of a cube root? Sure, okay, yeah. I'll do that on here. Okay, so where did my cursor go? All right, so we're talking about x to the 1/3, okay? And we're trying to take the derivative. So this is just a power rule. Power rule, yes, power rule. So power rule says the number comes out and then you subtract 1. So 1/3 minus 1. And then you just need to subtract 1/3 minus 1. So this is just subtracting a number from a fraction. Yeah, and so you get -2/3. So if your question is actually how do you subtract, how do you actually do this, I can show you that. How do I find the recitation videos? Yes, I made a separate channel just for recitation. So if you just look up Winston's recitation on YouTube, you can find the whole channel. I've made everything public. Unless somebody complains, then maybe I'll have to make it unlisted. But okay, so Dylan, did that answer your question? Okay, good. All right, any other questions? Okay, no questions. I'm gonna stop recording.